Okay, so we have finished talking about cases for static equilibrium and not in equilibrium. Now we want to focus on this part right here. We haven't fully elaborated what is this I right here. Okay, so to talk about I, let's move on to discuss more about rotational dynamics. Okay, let me zoom in a little bit. Okay, when we are talking about rotational dynamics, moment of inertia is very important. Okay, but to talk about moment of inertia is actually quite complicated because it's a concept which might be not familiar to you. You might feel alien about it. So what I think should be the easier way of explaining it is comparing it with mass. Compare. Okay, why do I want to compare this thing? Let's look at it. If we are talking about mass, we can think of mass as a quantitative measure of inertia. If you still remember Newton's first law, we can say that mass is a quantitative measure of inertia. So inertia is like resistance to change. Okay, remember the change in linear motion. Okay, what do we mean by change in linear motion? Is basically just acceleration. So mass is a resistance to acceleration. If you have a smaller mass, if you apply the same amount of force and you have a smaller mass, you have less resistance to accelerate. So you have greater acceleration. Okay? Smaller mass, less resistance, easier to accelerate. For another case, if you apply the same net force as just now, but this time your mass is very big. If your mass is very big, it means that you have a lot of resistance to acceleration. Therefore, the acceleration produced is very small. So that's the idea behind mass, and this is exactly the same idea for moment of inertia. Moment of inertia is resistance to change in rotational motion. So what does it mean is, if you exert a fixed amount of net torque, the net torque is fixed. If you have a very small moment of inertia, it means by this rigid body is not very resistant to angular accelerate. Means by you can easily change the rotational speed of the object. That's why the angular acceleration produced is large, because you can easily change the rotational speed of the rigid body. Rotational speed is basically just angular speed or angular velocity. So if you apply the same amount of net torque, but this time on an object, a rigid body with large moment of inertia, this rigid body will pose a very strong resistance to change in rotational motion. You have a strong resistance to change in rotational speed. That's why the angular acceleration produced is small. So that's the idea behind moment of inertia. How strong it resists the change in rotational motion. Okay, change in rotational motion is change in the angular velocity. Change in angular velocity is basically just angular velocity is basically just angular acceleration. Okay, so that's the usage of the purpose of having moment of inertia. So let's look a bit about the characteristic of moment of inertia. Moment of inertia depends on two things. The mass. Okay, mass is like if you have a very heavy mass, a very massive mass, a 1 kg object and a 1000 kg object. The 1000 kg object, of course, is harder to rotate. That's why greater mass, greater moment of inertia. Okay, it's harder to rotate. It's harder to rotate a tire compared to rotating a ping pong. Yeah, that's the idea behind it. So the next thing that moment of inertia depends on is the distribution of mass. So this one is a bit tricky. so you might not be able to imagine it, but if I change the position of the mass with respect to the axis of rotation, I can change the resistance of the object to change in rotational motion. So if you look at this case down here, I have two circular discs. If I concentrate my mass, the purple color is the mass, if I concentrate it to the center, okay, both of them are having the same mass. But if I concentrate the mass towards the axis of rotation, which is the black dot at the center, the mass are nearer to the axis of rotation. If you are nearer to the axis of rotation, you have a smaller moment of inertia. The thing will be easier to change in rotational speed. You can easily angular accelerate the object if the mass are near to the axis of rotation. Now, if you have the object of the same mass, but now you push all the mass to the rim of this object, it's like you push all the mass. Let's say this thing is filled with sand. Before this, you concentrate all the mass near to all the sand, you concentrate it near the center. Now you push all the mass, all the sand to the surrounding. If you push all the sand to the surrounding and you rotate it, you have greater moment of inertia. It's like it'll be harder to angular accelerate it. It's harder to make that thing start turning. It's harder to make that thing stop turning. It's harder to change the rotational speed of that object itself. Then we can say the object has greater moment of inertia. So that's the two things that the moment of inertia depends on: the mass and the distribution of mass. So if you combine the two things, you have this formula. I is the moment of inertia, and if you think of a rigid body as having a lot of particles, then you need to sum up the moment of inertia of each of the particles. Okay, if you have just one particle, then it's just mr squared. But if you have a lot of particles moving around the axis of rotation, what you can do is find the moment of inertia of each of the particle, then sum them up together. So you can see this mass is because of situation number 1. This r is the distance of the mass from the axis of rotation, is because of the distribution of mass. So together these two things forms the formula for moment of inertia. Okay, that's the moment of inertia formula for a collection of particles. But if you have a rigid body basically has a lot of particles inside it. If you want to calculate each and every one, the particle, what's their moment of inertia, then add down together, you can do until infinitely long when you are able to get the answer. So mathematicians use a bit of integration skill. They use a bit of integration, which is our syllabus. Then they are able to derive the moment of inertia for different objects and different axes of rotation. And this is the many formula that you can see in your notes. Okay, be careful. Moment of inertia depends on the axis of rotation. If you have the same object, but you change the axis of rotation to here, let's say you change it to here, then the moment of inertia will change. Okay, the moment of inertia depends on the axis of rotation. So if we want to look at the formula is like this. And there are many formula. There's no point to explain it. It's being derived using integration. But what you need to know is there are different shape, and for different shape there are different point of axis of rotation. Sometimes the axis of rotation can be on the side. Sometimes the axis of rotation can be at the center. So different situation, you have different moment of inertia equation being derived. You can refer here to these equations. These are the equations derived. These equations will be given to you in the question itself, so don't worry about it. The equation will be given, you don't need to derive it yourself. Okay, so that's the idea behind moment of inertia. If I have time, I'll probably produce one more video to explain moment of inertia, probably demonstrate to you moment of inertia. But that's it for moment of inertia. So knowing moment of inertia, you can apply it back to this sum of torque equals to I alpha, and you're able to study how the things rotate. Okay, you relate it back to 8.2 and 8.3. Okay, so with that said, let's move on to the last subtopic, which is on angular momentum.